Good day, class. Today we are going to discuss spring or mechanical spring. Mechanical spring is an elastic devices typically made from metal, designed to store and release energy, and it absorbs shock or maintain forces between two contacting surfaces. So, uh, when force is applied into a spring, of course, it deforms by either compressing, extending, or bending, depending on its type. So, and it returns to original shape when forces is removed. So, spring materials usually are used for high carbons, stainless steel, copper alloys, nickel-based alloys, steel alloys. So, um, usually, these are some of the materials that are used in mechanical springs. Okay. So for these are types of mechanical springs, compression springs. So compression spring here, which is the upper left, sorry, this one. So compression springs usually compresses under load. Usually found in if you're the pens, the pens, yes, and also in car suspension, you can also use that in other load-bearing devices. So that are for compression spring. So for extension spring, this one, so it's extension, so it stretches under load. It's often used in garage doors and trampolines, no? So the other type of mechanical springs are torsion springs. So torsion springs usually uh, it twists under load. So commonly used is clock or and also mouse traps and also hinges. So you can use that one. Okay. Or the other one is the leaf spring. So this one, the leaf spring, usually made of flat arc shaped sheet shaped metal layers. No, these are typically used in heavy vehicles or vehicles suspensions. Okay. And the last one is the constant force spring. It usually provides constant load over a range of motion and usually used in retractable devices. So these are some of it. Of course, the advantage and disadvantages of mechanical spring. Of course, the first one is the energy storage. So spring can store and release um, energy efficiently, making them ideal for applications where controlled energy discharge is required. For shock absorption, they absorb and dissipate the energy from impacts and vibrations. It also help protects sensitive components in a system, of course, in vehicles and machineries. It also force control. So springs can maintain consistent force um, to force retention between components that is useful in clamping, suspension system, and load-bearing structures. So also durability and reliability. Many springs are made from resilient materials that can withstand repeated compression, extension, or torsion. So it provides long operational lifespan. And of course, it is very cost effective and simple design because they are really relatively simple mechanical components. They are easy and inexpensive to manufacture and replace, and of course to repair. But the disadvantage of a spring is it limited the range of motion. Spring operates within a specific range beyond which they may deform permanently or fail, which can limit already with their application, which is not already usable. No, you material fatigue. No, over time with every time you use that and the continuous use, springs can lose their elasticity and it suffers from metal fatigue or it breaks and requiring again to replace or requiring maintenance. So additional cost if ever. So the heat sensitivity in high temperature environments, spring away materials can weaken, and it reduces already the effectiveness in energy storage and force maintenance also. So the size and space constraints. So spring needs physical space to operate within their designed uh, compression or extension range. So it can be a limiting factor in compact systems. And of course, the energy loss. So energy loss, it's during heat and compression, it reduces the overall efficiency of the uh, high precision application. Okay. And these are some of the advantages and the disadvantages of the springs, no? So these are some of the key properties that we need to know when we are dealing with springs. So the stiffness, the elastic limit, and energy storage. So stiffness, it indicates how much force is required to deform the spring by a certain amount. So it's represented by the Hooke's law, no? So for the elastic limit, the maximum extent uh, of the spring can be deformed without losing its shape. So this is the elasticity. And also for the energy storage, of course, the kinetic energy, no, the store energy when deformed through the kinetic energy. Okay, and also uh, these are some of the formulas for the springs, no. So the stress of coil spring, we have the mean diameter, the spring index, the Wahl's factor, uh, the spring rate, and also the deflection, the impact on flow on loads and spring. So these are some of the formulas, no? So you can still check your handouts for additional formulas. So So the usage of springs has a lot, no? So basically it absorbs energy or shocks load, no, to produce pressure and force to absorb. Okay, you also have the uh source of energy also, no? So spring is a very versatile component in machine design, okay? So it also gives you you can also check the other your handouts now for some of the formulas that are used. Okay, so we're gonna solve or your addition. I know we solved already during our class. So these are the additional problems I'll give you. Okay, so this are our uh, additional problems. So a crate mass of 1,800 kilograms is moving at a speed of 1,200 meter. Well, sorry, 1.2 meters per second. It is brought uh, to rest by two helical compression springs. In stopping the crate, the springs are compressed 200 millimeter. If the spring has a spring index of 6 and an allowable stress of 360 megapascal, we look for the Wahl's factor. Sorry, Wahl's factor, the wire diameter, the outside diameter, and the mean diameter. Okay, so we'll look for the Wahl's factor first. So in order for you to get the Watt's factor, the formula is equals to 4C minus 1 over 4C minus 4 plus 0.615 over C. So C is the spring index. So 4C, you already have the spring index, which is 6. So you just substitute 4 times 6 minus 1 over 4 times 6 minus 4 plus 0.615. Okay, so the answer here is 1.25. Okay, next, we have the wire diameter. So in order for to get your wire diameter, you need to get the velocity, okay, or the acceleration also. So the wire diameter is equals to D is equals to the square root of 8 kf, the spring index over pi 360 s. Okay, so we look for A in order to get the force, no? So we don't have the force, so F is equals to ma. Okay, so we don't have A, but we have M. So in order for to get A is equals to the velocity, initial velocity minus the next, no, 0, 2 over 2s, the distance. Okay, so V we don't have 0 minus 1.2 moving 1.2 over 2, and then it's how much? 200. So 0.2. So the acceleration is 3.6 meters per second squared. So you have M, which is 1,800 kilograms. So we can get already the force. Force is equals to 1,800 multiplied by 3.6 meters per second squared. So our force is 6,480 Newton. So the diameter, the mean diameter uh, is 6. The mean diameter is C, spring index D. So dm is equals to 6D. So from here, we can get our small d, okay? So you have 8 times 1.25 times 6,480 multiplied by 6 all over pi times 360. So the diameter is, or the wire diameter is 19 millimeter. So next, the outside diameter, which is the O, is equals to spring index multiplied by D plus D. So we have C, which is 6 times 19 plus 19. So that would be, so 16, 6 times 19 plus 19. So the outside diameter is 133 millimeter. Okay, so lastly, the wire diameter, the mean diameter, we'll get it at outside diameter minus D, or 133 minus 19 equals to 114 millimeter. Okay, so we already had the mean diameter. The mean diameter. We have the outside diameter. Then you have the wire diameter. And we have the wall factor. Okay, next, we solve for the next, which is the smaller of two concentric helical springs is made of 22 millimeter diameter steel spring and has an outside diameter of 100 millimeter, with 10 active coils. So the outer spring is made of 32 millimeters steel spring and has an outer diameter of 250 with 8 active coils. So before the load is applied, the outer spring is 25 millimeter longer than the inner spring. So if the load of 90 kilonewton is applied to this nest of spring, we find for the spring index of the inner spring, the spring index of the outer spring, and determine the spring rate of the inner spring in kilonewton meter. Okay. So to get the spring index, so for of the inner spring, we have C equals to the DO minus D over D. So for this the inner spring, we have the outside diameter of 100 and diameter is 22. So we just direct substitute. So 100 minus 22 over 22. So it would be 3.545. Okay. Next, B, we have the outer one. So we have DO minus DO, so over D. So for the outside diameter for the outer spring, we have 250 and 32. So we just 250, 250 minus 32, 250 minus 32 over 32. So that would be 6.81. Then lastly, the spring rate of the inner springs. So in order for us to get that, the formula is GD over 8C cubed number of atoms. So that would be G is given 80 million multiplied by 0.022 and then 8 times the inner is 3.545, 3.545 cube times 10. Okay, 10 active coils. Okay, so that would be Ki is equals to 493, sorry, 0.8 kilonewton per meter. So this is the one. Okay. Okay, so the previous one that we've discussed is this. So I'll just look at this one. So the tree extension, coil spring or hook in a series that support single weight of 150 kilograms. The first spring is rated at 0.4 kilograms per millimeter and the other two lower is rated at 64 kilograms per inches. So compute the total deflection. So in here, the force is the same if it is in series. So if it is in parallel, the deflection is equals. Okay, so that is the difference between the two, the coil, the spring in parallel and the spring in series. Okay, so we already discussed this one, so you can just check this out. So the next problem was to compute the maximum deflection of a 20 coils helical spring having a load of 100 kilograms. The spring is squared, the ground end modulus of elasticity shear of 85 gigapascal, outside diameter of 105 millimeter with diameter of 10.5. So we already discussed this one. So you can take a look of what we've how we've done it. Okay. Okay, then next we also have the computed deflection of 18 coils helical spring having load of 100 kilogram. The modulus of velocity in shear of spring is 100 gigapascal. Outside diameter of 10 with the diameter of 10 millimeter. The spring is square and ground end. So from here, you can check this out. Okay. Then the last one, high alloy spring having square ground end. That's a total of 16 coils and the modulus of velocity in shear of 95 gigapascal. Compute the wall factor. The spring outside diameter is 10 centimeter and the wire diameter is 1 centimeter. So you can check this out. So we just direct substitution. Okay, and then the last one, Compute the deflection of an 18 coil helical spring having a load of 100 kilogram. Oh, sorry, this is the one that I just discussed. Okay. So these are the topics for spring. So have a good day. Thank you. These are the one. Okay.